Hello everyone. In a power transmission system, there are active power transfer and reactive power. The reactive power losses are occurring in the transmission system due to the inductance and capacitance present in the system. In order to improve the power transfer capability of a power system, we are using flexible AC transmission system or FACS controllers. The control of power flow in AC transmission line is determined by equation P max equal to V1 V2 by X sine delta, so that we can control the active power by controlling the reactive component X or by controlling the power angle delta up to a limit with a constraint of thermal and stability limit. A flexible AC transmission system is the involvement of power electronic components in the power system. Or a flexible AC transmission system is defined as alternating current transmission system incorporating power electronic controllers to enhance the controllability and power transfer capability. The power electronic converters are involved in the power system to enhance the power transfer capability of the system. There are different types of flexible AC transmission system depending on the connection. They are shunt connected, series connected, combined series, combined shunt series. In shunt connected controllers, mainly it injects the current into the system at the point of current connection, and in series connected controllers, it injects voltage in series with the line. And in shunt series, both voltage and current can be injected, and in series, it is possible to balance both reactive and real power. So flexible AC transmission system composed of static equipment used for AC transmission system. As it is power electronic converters, there is no moving parts in the system. It increases the reliability of AC grid. They improve the power quality and transmission efficiency from the generation through transmission down to private and industrial consumers. Better utilization of the network as the power transfer capability is increased, and increased availability and reliability, as well as improved network stability with a higher power supply quality. The need for flexible AC transmission system. The power transfer capability of the system is increased by using back controllers. Power flow is kept over and under designated routes. The power flow through the lines can be controlled, and also it improves the power quality in terms uh, means the quality of the voltage and current waveform produced. The voltage and current should be sinusoidal with 50 hertz frequency. There may be chance of harmonics or some other noises in the voltage and current waveforms that can also be avoided by using flexible AC transmission systems. The main benefits of fast controllers are the reactive power flow in the line can be decreased and the lines are made to carry more active power. The power flow in the transmission line can be made optimum. It controls the line impedance angle and voltage, which helps in controlling the power flow in transmission line. As we have seen in the power flow equation, power flow can be controlled by controlling the angle, impedance angle, and also by controlling the reactive element. It supports the power system security by increasing the transient stability. By keeping the frequency constant or by avoiding the power quality issues, we can make the system stable. This also limits overloads and short circuit currents. The loading capacity of the line is greatly increased. As the power transfer capability increases, loading capacity increased. Thus, upgrading of lines is possible. It limits the impacts of faults and equipment failures. It helps in reducing damage of various equipments. There is increase in the utilization of low cost generation due to cost effective enhancement of transmission line capability. Efficiency increases. It helps in damping out oscillations and avoid damage of various equipments connected to the transmission system. As we have seen in the first slide, there are different types of controllers, PAX controllers. Mainly two classification is shunt connected and series connected controllers. Static var compensator is a shunt connector controller used in fact devices. Other than static var compensator, we have STATCOM. Different shunt connected controllers are available. The commonly used is static var compensator or SVC. So SVCs are part of flexible AC transmission system family, which regulates the voltage, improves the power factor, reduces the harmonics, and stabilizing the system. Harmonics are components, current or voltage components with multiples of actual frequency. A static or compensator has no significant moving parts as it is power electronic components. There is no moving parts. The SVC is an automated impedance matching device designed to bring the system closer to unity power factor. So power factor can be increased up to unity. The main purposes are it will regulate the transmission voltage and in a power system, and also in industrial loads it improves the power quality or improves the power factor. In transmission application, SVC is used to regulate the grid voltage. Grid voltage can be regulated if the power system reactive load is capacitive. The SVC will use thyristor control reactor to consume power from the system, lowering the system voltage. If it is leading load, the lagging load is provided and the system voltage can be adjusted. If it is lagging load, leading compensation can be provided to adjust the system voltage. Always the reactive component is related with the system voltage and the active part is related with the system frequency. Under inductive lagging condition, the capacitor banks are automatically switched in, thus providing a higher system voltage. So, if it is lagging, capacitor banks are used. Variable capacitor banks are used. By connecting thyristor controlled reactor, which is continuously variable along with the capacitor bank, net result is continuously variable leading or lagging power. So, a thyristor controlled reactor is a part of static var compensator, which controls the reactance, inductive reactance by using a thyristor arrangement. For industrial application, SVCs are placed near high or rapidly varying loads like arc furnaces. SVC comprises of one or more banks of fixed or switched shunt capacitors or reactors and at least one bank with switched by thyristors. So this figure we can see the configuration of a static var compensator. It consists of two filters, a thyristor controlled reactor and thyristor switched capacitor. This is a capacitor which is switched by using thyristor. And this is inductance which is controlled by using thyristor arrangement. This thyristor back-to-back arrangement acts like a AC voltage controller. So it controls the voltage or output of the AC by this back-to-back arrangement. So SVC configuration employing a thyristor controlled reactor and thyristor switched capacitor and a harmonic filter is shown here. There is thyristor switched capacitor and thyristor controlled reactor. With proper coordination of capacitor switching and reactor control, the VAR output can be varied with capacitive and inductive ratings of the equipment. Depending on the requirement of the load, this reactance and the capacitance value can be varied by adjusting the control signals to the power electronic converters. or this back-to-back converter, back-to-back thyristors. The compensator is normally operated to regulate the voltage of transmission system at a selected terminal. So mainly it controls the control functions like it will always maintains the voltage constant at the point of connection. Always this controller will check whether it is constant or not. So according to that, control signals are provided to the thyristors and the reactive elements can be varied. Next is fixed capacitor thyristor control reactor. This is also a part of static work compensator. Similar to that, fixed capacitor thyristor control reactor consists of a shunt connected capacitor in parallel with a thyristor control reactor. So there is a capacitor and thyristor control reactor. The thyristor control reactor continuously control the reactive power for lagging power factor. This system is mainly used for lagging power factor only. To extend the dynamic controllable range to leading power factor domain, a fixed capacitor bank is connected in shunt with the thyristor control reactor. So this part will compensate only lagging power factor. So in order to make the range to leading power factor, this capacitor also added in parallel with the thyristor control reactor. So the fixed capacitor bank usually connected in star combination. It will be connected to the three-phase supply. So even though it is shown as a single phase circuit, there will be three capacitors for three-phase supply. The capacitance will be connected usually in star configuration. Each capacitor contains small tuning inductors that are connected in series and tunes the branch to act as a filter for harmonic order. In some cases, there will be inductors or additional LC circuits for tuning the system for avoiding the harmonics. As in SVC, we have seen some harmonic filters also provided here without thyristors. This will filter the harmonics that will be tuned for particular frequency. That means if third order harmonics, it will have a 150 hertz frequency that will be avoided by setting the parameters of inductance and capacitance here. That will be tuned for 150 hertz frequency. So 150 hertz frequency will be bypassed from the circuit. So this is a fixed capacitor thyristor control reactor circuit. So in a thyristor control reactor circuit, the power electronic component is AC voltage controller circuit with two thyristors connected in anti-parallel. So the voltage can be controlled like this. Always, since it is inductive, the current lags behind voltage by 90 degree. So the output voltage can be varied by using this arrangement. Next is series compensation. So static VAR compensator is shunt and series compensation. We will be connecting the back controllers in series with the line. Series compensation is a method of improving the system voltage by connecting a capacitor in series with the transmission line. In other words, series compensation reactive power is inserted in series with the transmission line for improving the impedance of the system. It improves the power transfer capability of the line. It also improves the system stability, similar to shunt compensation. It acts all the purposes, serves all the purposes. It is mostly used in extra and ultra high voltage lines. Thyristor control series capacitor or TCSC is a uh, series compensation, model of series compensation. Over here we have TSSC and TCSC, thyristor switched series compensator and thyristor control series compensator. In thyristor switch, the capacitance is connected in series with the line and it is switched according to the operation of this thyristors. In thyristor control series compensator, there will be additional inductance along with the thyristor connection so that we can control the value of reactive components XL minus XC by using this arrangement. So it is a compensator consisting of series compensating capacitor with parallel connected thyristor controlled reactor. It is one of the fact device which are mainly used for control of active power flow in system, increase in transmission power line capability. TCSC is involved in a series to line and is allowing changing the impedance of transmission path N, thus affecting the power flows. Mainly, it changes the reactive impedance of the system by changing the value of capacitance and inductance. The control is fast, efficient, and increased between the transmitted powers. The basic scheme of TCSC or the resistor control series capacitor is shown here. In actual case, there will be number of capacitor and inductor combinations connected in series. So we will get a smooth control possibility with a fixed capacitor here. And also actual TCSC consists of some protective equipments along with the series capacitors. So series capacitor is used primarily to minimize the cost and more increase the efficiency of the system. So C1, C2, Cn are different modules, maybe have different values. So we will get a wide range of reactive power control. The change of impedance of TCS is achieved by changing the thyristor controlled inductive reactance of the inductors connected in parallel to the capacitor. So by changing this inductance, we can control the impedance. So this is the main component or series compensator used in fact controllers, that is TCSC. So in this video we have discussed about fact controllers, working of fact controllers and different types of fact controllers including series and shunt compensators. Thank you.